Imagine you drop a detective into like just a totally chaotic, sprawling crime scene.
Oh, a total mess.
Yeah, right. Like there's a broken window, mud on the carpet, maybe a half-eaten sandwich on the counter, and just fingerprints everywhere.
Right.
Now, instead of telling them, to look for a specific murder weapon, you just say, find something interesting.
Dude, freeze.
Exactly. They would completely freeze. I mean, they'd have no idea where to start, what clues actually matter, or, how to separate the random noise from the actual story of what happened. And for decades, artificial intelligence has had that exact same problem.
It really has. I
Okay.
mean, it's what we call the curse of open-ended environments.
Right.
Because if you just hand an AI a massive database and say, hey, discover a new scientific law,
Mm,
it gets completely overwhelmed by the sheer volume of possibilities.
yeah.
It fundamentally needs a human to point to that broken window and say, start right here.
Which is basically the core problem we're tackling for you on today's deep dive. We're looking at a stack of sources today anchored by this really provocative new research paper.
It's a fascinating one.
It really is. It's titled Autonomous Scientific Discovery via Iterative Meta-Reflection. It was developed by researchers over at the University of Edinburgh and MIT. And the mission for us today is to figure out if AI can finally step out of its traditional role.
Right, because we know it can summarize human knowledge.
Sure, we know it can write emails and like draft code,
Yeah.
but can an AI look at a massive pile of raw, totally unstructured data, figure out what questions to ask without any human guidance, and actually prove its findings mathematically?
Well, the current state of AI science tools would definitely suggest no,
Yeah.
because most systems fall into this very narrow search space. Like take classical structure learning methods, for example.
Okay.
They are incredibly rigid. They generally just look for really simple cause and effect pairs, what scientists call pairwise relationships.
Let's ground that for a second for everyone. When you say a pairwise relationship, you basically mean the AI is just running down a giant checklist asking, like, does variable A affect variable B? Does A affect C?
That's exactly it. It's this brute force approach to finding really basic correlations.
Mm-hmm.
I mean, it might figure out that taller plants get more sunlight,
Sure.
but it completely fails to express higher order patterns. It can't identify a complex chain of events or realize that maybe a hidden third variable is actually controlling both A and B.
So going back to your detective analogy from earlier.
Yeah, classical AI is basically like a brilliant forensics tech.
Okay.
If you hand them a glass and say, test this specific glass for fingerprints, they are absolutely flawless.
Yeah.
But they cannot just survey the entire room and develop a working theory of the crime.
Until now, supposedly, right?
Right.
Because this new paper introduces a framework called DiscoPER, which is basically designed to be that lead detective. It's an autonomous large language model-powered system built for truly open-ended research. And to grasp how it actually pulls this off, we really have to pull apart its core engine. It runs on this very specific three-step loop: propose, evaluate, and reflect.
Right, and the propose phase is where that whole blank slate approach really shines.
How so?
Well, the system starts with completely unstructured multimodal data. So we're talking raw spreadsheets mixed with just folders of images.
Okay.
And crucially, nobody gives it an objective.
Yeah.
The AI agent just scans a basic summary of the data schema, and then it generates a hypothesis in natural language.
Yeah, it just writes out a guess.
Exactly.
Yeah.
But, a text hypothesis isn't enough to actually do science.
Mm-hmm.
So the AI then writes the executable Python code necessary to test that exact claim against the massive data set.
Okay, I have to stop you there because anyone who uses large language models knows the glaring issue here.
Hallucinations.
They hallucinate constantly. I mean, an LLM will confidently tell you that the sky is neon green if it gets confused.
Oh, absolutely.
So if the AI is generating its own hypothesis and writing its own code, how do we know it isn't just hallucinating a scientific fact, writing a piece of Python that looks smart and declaring a bogus breakthrough?
Well, that skepticism is exactly why the evaluate step is built the way it is. It's basically the anti-hallucination mechanism.
Okay, walk me through that.
DiscoPER never relies on the language model's internal confidence to judge whether a claim is true. The Python code it writes must be executed against the actual data.
So it forces it to show its work.
Exactly. First, it runs the code on a training split of the dataset to calculate statistical significance.
Meaning it checks the p-value to see if the signal is real or just some random fluke in the data?
Right. But it also checks the effect size.
Okay, what's the difference there?
Well, significance tells you if a pattern exists at all, but effect size tells you if it actually matters in the real world. It ensures the AI doesn't flag some microscopic, totally meaningless mathematical blip as a grand scientific discovery.
But wait, if an AI is generating like hundreds of hypotheses really fast, isn't it just kind of throwing spaghetti at the wall?
Yeah, that's a risk.
Because even with statistical tests, if you test enough random things on a data set, you're eventually going to find false positives. Like the math will just check out by sheer dumb luck eventually.
You're touching on a massive problem in human research called p-hacking,
Right.
where you basically just torture the data until it confesses to something.
Ah, that's a great way to put it.
But DiscoPER prevents this with this brilliant failsafe,
Right.
because passing the statistical tests on that initial training data, it's not enough.
What else does it have to do?
If the code succeeds there, the system is forced to run the exact same Python script on a completely separate, held-out validation data set.
Oh, wow.
Yeah. If the hypothesis doesn't hold up on data it has literally never seen before, it gets thrown out entirely. So it basically guarantees the discovery is mathematically grounded in reality, not a statistical fluke or some wild LLM hallucination.
Man, that is a really rigorous filter.
It has to be.
But, a filter only removes the bad ideas, right? It doesn't actually help you find the good ones. If the AI is just blindly guessing and getting rejected by that validation set over and over, wouldn't it just get stuck?
It would.
So how does it know when to change tactics?
Well, it needs an overarching strategy, which brings us to the true breakthrough of this paper, the reflect module.
Okay.
The researchers actually refer to it as second-order meta-reflection. So imagine the system has run through 50 cycles of proposing and evaluating.
Right.
It now has a pile of validated claims and a pile of rejected claims. Every 5 iterations, the system forces itself to just pause. A separate LLM agent steps in and analyzes both of those piles.
So it treats its own past successes and failures as a brand new data set to study.
Exactly.
I'm trying to visualize this. It's kind of like a hiker trying to navigate a mountain range in heavy fog.
Oh, I like that.
Like if you just look at your feet, you might walk up a small hill, reach the top, and just assume you found the highest summit.
Right. Which machine learning engineers actually call getting stuck in a local maximal.
Yeah.
You optimize for your immediate surroundings, but totally miss the bigger picture.
Exactly. You need a way to look at like a satellite map and realize, oh, wait, I need to hike 10 miles west to find the actual mountain.
That's a perfect way to visualize the reflect module. It acts as that satellite map. It analyzes its own trajectory to identify structural gaps or confounding variables.
Does it actually work like that in practice?
We actually see it happen mechanically in the paper's logs. In one of the early runs, the system kept testing hypotheses related to a variable called positional accuracy.
Okay.
And it failed statistical validation every single time. Now, a classical AI would just keep tweaking that variable endlessly, basically trapped on that small hill you mentioned.
Because it lacks the overarching context to know it's a dead end.
Exactly.
Yeah.
But DiscoPER's reflect module saw that pattern of failure. It generated a meta-reflection that explicitly instructed the system, saying, positional accuracy is yielding a 0% success rate. Abandon this variable. Yeah, and it said, shift your focus to kingdom-level geographic comparisons instead. It actively charted a new course away from a dead end with literally zero human intervention.
That is just fascinating in theory. But a pristine laboratory setting is one thing, right?
Sure.
You can't evaluate an autonomous scientist with a clean, pre-packaged multiple choice test because providing the test itself violates the whole rule of having no human-guided objectives.
Right, you'd be pointing out the window again.
Exactly. So
Yeah.
to see if this actually works, you have to unleash it in a messy environment.
You need a real-world sandbox. So the researchers created an entirely new benchmark from scratch. They called it iNatDisco.
iNatDisco. Okay.
And they sourced this from iNaturalist, which is this massive citizen science platform. We are talking about tens of thousands of everyday people hiking through the woods, snapping photos of bugs, plants, and animals with their smartphones.
Yeah, the scale of the data here is just wild.
Oh, totally.
Because they built two distinct sets for this, right? Like a smaller one with 800 observations, and then a massive one with 50,000 observations covering nearly 10,000 different species.
Yep.
And what's crazy is this isn't just a spreadsheet. It combines tabular metadata, so the latitude, longitude, and timestamps of the observations, with the actual raw photographs.
The visual element is key.
But if the AI has no instructions, how do the researchers actually score its performance? Like, how do you measure a discovery?
Well, they seeded the sandbox. The researchers combed through peer-reviewed ecological literature and identified established, verified patterns that exist within this specific data.
Like what?
For instance, the well-documented fact that monarch butterflies migrate north during the spring and summer. They hid these ground truth patterns in the dataset.
So they already knew the answers.
Exactly. But the AI is never told to look for butterflies or migrations or seasons. The test is simply, will the system organically stumble upon and mathematically prove these verified ecological realities?
Okay, the scorecard on this is staggering when you look at it. Because when the researchers unleashed classical causal AI models on the data, those systems found, at most, 1 out of the 9 hidden patterns.
Right, a near total failure.
They fundamentally failed to navigate the open-ended space. But DiscoPER, it successfully discovered 8 out of the 9 hidden patterns on the 800 observation dataset.
Yeah.
And on the massive 50,000 observation set, it found 8 out of 12.
Which is incredible.
More importantly, I think, nearly 73% of the novel hypotheses it proposed passed that brutal unseen validation test we talked about.
And that 73% hit rate. That is almost unheard of for a completely unguided exploration. And to prove why it succeeded where the classical models failed, the researchers conducted an ablation study.
Remind me what an ablation study is again.
That's where you systematically turn off components of the system to isolate what's actually driving the performance. So when they disabled the reflect module, the system degraded instantly.
Oh, really?
Yeah.
Yeah.
92% of the hypotheses it generated just became incredibly basic, low-level claims.
So it regressed. It basically went right back to being that lazy forensics tech, just checking to see if variable A was bigger than variable B.
Exactly. It lost the ability to strategize.
Yeah.
But with the reflect module active, those basic hypotheses dropped from 92% down to 69%.
Wow.
The system began proposing complex interactions and compound theories. For example, rather than just testing fungi against latitude in one test and plants against longitude in another, the reflect module synthesized its previous fragmented findings.
So it stitched them together.
Right. It formulated a unified hypothesis that combined latitude and longitude to test for spatial niche separation between entire kingdoms of life.
It realized that looking at a 1D line just wasn't enough, so it started mapping life on a 2D grid to see if, fungi and plants occupied entirely different geographic territories.
And it wrote the Python code to prove it.
That's insane. But here's where I feel like we really need to dig into the mechanics of how it actually did that. Because up until this point, we've mostly talked about the spreadsheet part, right? The latitude, the date, the species name.
Right.
But you mentioned the data includes actual photographs. How on earth does an AI combine a static spreadsheet with a visual photograph to perform a statistical test?
Yeah, this is perhaps the most elegant part of the entire framework. During the proposed step, DiscoPER can actively call upon a vision language model, or VLM.
Okay.
This allows the system to extract qualitative visual attributes from the raw images and mathematically engineer them into brand new testable variables.
Let's break down exactly how that translation from image to math happens, because the mammals versus plants example they give in the paper is just mind-bending.
It perfectly illustrates the mechanism. So the AI sent photographs of red foxes and red deer to the VLM. The vision model returned a text description noting these animals were found in, quote, expansive terrain, scrubland mountains.
Okay.
Then it analyzed photos of dandelions. The VLM described the visual context there as sessile, rooted in place, grassy area.
Right, but sessile and rooted are just strings of text. And a statistical script requires numbers, or at least distinct categories. You cannot calculate the standard deviation of a sentence. So how does the AI bridge that gap?
It writes code to mutate the dataset.
Wait, what?
Yeah, the system takes those qualitative text observations and engineered a brand new categorical feature. It literally writes a Python script to add a new column to its own spreadsheet. Let's call it a mobility index.
Oh, wow.
It assigns the dandelion a 0 for being rooted and the red fox a 1 for moving across expansive terrain.
That is so clever.
Right. Now, it has a newly minted quantitative variable. It can run a statistical regression comparing that new mobility index against the variance in the longitudinal coordinates.
And the result of that math.
It proved that mammals have a significantly wider geographic spread, a standard deviation of 22.1 degrees in longitude compared to plants, which were restricted to 8.3 degrees.
So it mathematically proved that large mammals roam further than plants, starting just from looking at a picture.
Exactly.
And it executed a similar workflow to separate fungi and flowering plants, didn't it?
It did. The VLM processed images of fungi and noted they appeared on, quote, mossy forest floors with dense canopy in a damp, cool, humid climate. Conversely, it saw dandelions in open ground with sparse vegetation.
Right.
It engineered those visual contrasts into variables, tested them against the GPS metadata, and successfully proved a biogeographic reality. Fungi occupy a significantly higher latitude ecological niche than flowering plants.
That is wild.
The mean latitudes for fungi was 52.5 degrees north compared to just 44.2 degrees for the plants.
I really want to make sure the gravity of this lands for you listening right now. Mossy forest floor, dense canopy. None of those words existed in the original dataset.
Nope, not at all.
The AI extracted them purely from the visual background of a user's smartphone photo. I mean, it acted exactly like a human ecologist wandering through the woods with a notebook.
Exactly like that.
It observed the environment, recognized a qualitative difference in habitats, converted that observation into a quantifiable metric, and then ran the math on the GPS coordinates to prove its theory.
It is a seamless chain of reasoning. It bridges qualitative observation directly with quantitative statistical proof.
Okay, but we have to address the massive, glaring elephant in the room here.
Let's hear it.
And it's a doubt I've honestly had since we started unpacking this. Large language models are trained on the entirety of the internet. They have essentially memorized Wikipedia.
Sure.
So if I open a basic chatbot right now and ask about monarch butterflies, it already knows they migrate.
It does.
So how do the researchers prove that DiscoPER is actually making empirical discoveries based on the data in front of it? What if it's just cheating?
It's a great question.
Like, what if it already knows the answer from its training weights, and it's just writing Python code to confirm what it already memorized?
It is easily the most critical vulnerability in the entire framework. Are we witnessing genuine scientific discovery, or are we just watching a very sophisticated search engine regurgitate pre-trained facts?
Exact.
To settle this, the researchers engineered a brilliant trap. They designed a counterfactual evaluation using a manipulated data set they called INET Disco 800 CF.
CF meaning counterfactual, so they intentionally broke reality.
Yes, they did.
What exactly did they do to the data?
They went into the spreadsheets and maliciously altered the underlying metadata to completely contradict real-world ecology.
Oh, wow.
Yeah, they swapped timestamps and inverted GPS coordinates.
Yeah.
So in this counterfactual data set, birds do not migrate seasonally.
Right.
And fungi, which in the real world fruit heavily in the autumn, were manipulated so that 77% of their observations occurred in the spring.
So they created an absolute bizarro world ecosystem, but they left the photographs alone.
Exactly. The visual data remained intact, but the mathematical reality of the spreadsheet was totally inverted.
Okay, I see where this is going.
This creates a direct conflict for the AI, because if the system relies on its massive neural network of prior knowledge, its Wikipedia memory, it will generate a hypothesis claiming that fungi peak in the autumn, because that is the factual truth of the real world.
But if it tests that hypothesis against the bizarre manipulated data, the evaluate module will reject it because the math won't support it anymore.
Exactly.
So what happens when the LLM's brain clashes with the Python script's math? Like, who wins?
The math wins.
Really?
Yes.
Huh?
DiscoPER successfully reported the counterfactual patterns. It suppressed its own pre-trained knowledge and proved that, within the confines of this specific strange dataset, fungi peak in the spring and birds do not migrate.
That is the ultimate trump card right there.
It really is.
It proves its loyalty is entirely to the empirical evidence in front of it. Even when the data directly contradicts everything it learned during its initial training, it follows the math. That proves it's actually doing the science.
It isolates the framework's ability to reason from evidence, rather than relying on memorization. Though I should mention, the researchers did note one fascinating limitation regarding the scale of this exploration.
Oh. What kind of limitation?
They found that as you let the system run longer, say up to 100 iterations of that propose, evaluate, reflect loop, it does find more total patterns. Its overall recall goes up.
Okay.
But its success rate, like the percentage of hypotheses that actually pass the validation phase, steadily drops. It falls from around 98% in the early loops down to about 64% by iteration 100.
Wait, why the drop-off? Does the reflect module start to break down or get confused?
Not at all. The drop-off is actually evidence that the reflect module is working exactly as intended.
How so?
Well, in the first 10 iterations, the AI tackles the most obvious, statistically dominant patterns in the data, the massive correlations.
The easy stuff.
Exactly. Once those are exhausted, the reflect module pushes the AI out into the margins. It forces the system to explore highly subtle interactions between esoteric variables. Naturally, when you are operating on the bleeding edge of the search space, formulating complex speculative hypotheses, a higher percentage of those guesses are going to fail the statistical validation.
It's the apple orchard analogy.
Oh, yeah, explain that.
Like when you first walk into the orchard, you spend 10 minutes grabbing all the low-hanging fruit. You have a 98% success rate of getting an apple in your basket every time you reach out.
Right.
But by hour 3, you are balancing on the top rung of a ladder, reaching for a tiny weird apple at the very top of the canopy. You're going to drop a lot more of them. But if you want to harvest the entire tree, you have to be willing to reach for the speculative fruit and fail a few times.
Exactly. A dropping success rate isn't a bug. It's the cost of doing exhaustive, truly open-ended exploration.
Man, we have covered incredible ground today. Let's pull the lens all the way back. For you listening right now, the core takeaway from this stack of research is a fundamental shift in how we view artificial intelligence.
It really is a turning point.
We are moving way beyond the era of the AI chatbot just summarizing PDFs for us. With systems like DiscoPER, we are witnessing the architecture for an autonomous research assistant. A framework that can ingest massive, messy, multimodal data sets, synthesize qualitative visuals into testable math, generate entirely original questions, rigorously validate its own code, and use its failures to navigate away from dead ends.
And, it's crucial to frame this correctly. This does not replace the human scientist.
Right.
A human must still determine the ethical implications, secure the funding, and apply the findings in the physical world. What this does is scale our capacity for hypothesis generation.
It's accelerant.
Exactly. It acts as an untiring collaborator that surfaces deeply buried high-level patterns in data that a human researcher simply does not have the computational bandwidth, or really the lifetime, to uncover manually.
It is the ultimate detective's assistant, constantly surveying the crime scene, rearranging the clues on the whiteboard, and doing the statistical heavy lifting while you sleep. But I want to leave you with one final provocative thought to mull over.
Oh, I like these.
Everything we explored today, the biogeography of fungi, the geographic spread of mammals, it was tested on static historical data. The researchers downloaded a fixed snapshot of the past.
Right.
But what happens when an autonomous, self-reflecting, code-writing scientific system is no longer confined to a downloaded spreadsheet? Imagine hooking this framework up to live streaming data.
Oh, wow.
What if this AI was tapped directly into global satellite feeds, real-time ocean temperature sensors, or live epidemiological data streaming from hospitals worldwide?
The scale of that would be unimaginable.
If it can uncover hidden ecological truths from old smartphone photos in a single afternoon, what invisible world-changing phenomena might it discover when it is watching the planet in real time?
That is the true frontier. The bottleneck is no longer data collection. It's our ability to process it. A system like this could accelerate the pace of scientific discovery in ways we can barely even quantify.
It's like we finally built a detective who can view the entire world as one giant interconnected puzzle. Now we just have to wait and see what they find. Thanks for joining us on this deep dive. We'll catch you next time.